Let us, so welcome to this lecture 21st, stability of structure. So let us briefly recapitulate what we have done. So we started with dynamic stability, and we have almost reached to the end actually of this chapter. So we have studied a number of cases, starting from fall-over force, and then gyroscopic stability, right, and then parametric resonance, and then aerodynamic flutter, and then we have also considered the noise stabilization of system, and the last example, that was noise stabilization of system. That's what we are illustrating using briefly. We are illustrating using the stability of this stick on kept on palm, right. So what I was just trying to demonstrate to you is that this is an example of noise stabilization. I've seen that in this stick, when if I want to hold in my palm, right, on my so then what we have to do, you see, when it is trying to fall, right, then I have to take it down, right, and when it is trying to so the way this, so for stabilization of this stick against falling, right, I have to move this thing in the vertical plane, and then what we have established clearly that so here was the stick, that was simple model that we have considered. So here was the mass, right, and then this is rigid, this was length L, and then we are giving excitation here, right. So U double dot, right, and we have considered that the degrees of freedom when we solved it mathematically, this is the theta, right, and then there was these two frequency of this system. One is of course the frequency of oscillation for this, for the stick, right, that's what, right, this stick when we are going to put, because of its mass it is trying to fall, right. So that will have a frequency omega 0, and then you are going to excite this using some frequency omega. So for stability, I have shown that there was some condition, then omega need to be very large comparing omega 0, right. And of course there was some other, in this inequality, some other parameters were also involved, that was nothing but this length L, and then the amplitude of this excitation and others, right, amplitude of excitation. So essentially what is happening, what I see, whenever this is trying to fall, then you have to take it downward, right, so that this theta reduces, and then when it is trying to come too close, then you just try, when it is trying to fall this side, right, it is getting destabilized, then you have to take it down, and then when it is coming and crossing it, once you try to fall, then you just have to take it upward, right. So essentially what there are two time scale in the motion that was competing. One is that of course we have this periodic motion that is dictated by this frequency omega 0. If we plot theta, and then with time, then this frequency, this time period, the characteristic frequency for this is the omega 0. Okay, so this is the slow frequency. On the top of that, because of this excitation omega, all these small oscillations are are riding on these things, riding on, and what they are essentially doing, as soon as this is trying to destabilize it, okay, this noise is trying to bring it down, you understand, and that's why this noise stabilization is occurring, right, and that this I have established mathematically using a very simple mathematical argument that you must have seen on the previous, right. So this is not that only the, see, I was just trying to explain this with a very simple stick example kept on palm, right, but then please note that there are many examples of this kind of noise stabilization, especially in other physical systems, right, in physics, and when we ride bicycle, that is also nothing but a noise stabilized system. Okay, good. So now one more thing I am going to briefly mention to you. We have already briefly touched when we discussed this aerodynamic instability. We have introduced the concept of this self-exciting force, and then aerodynamic, the flutter derivative and others, right, which basically correlates the exciting force with the response of the structure, because all these excitation, that's why we call it this excitation to be parametric, because excitation the force that is being applied on the system, can modify, is basically dependent on the deformation of the structures, right. So that basically creates a loop, right, for the feedback loop, right, through which they interact basically. The deformation of the elastic deformation of structure interact with the aerodynamic loading, and those were described using simplified model, and then finding out this aerodynamic flutter derivative, right. And then we have taken the example, simplified example. Of course, we deal with this reduced order model for the Tacoma bridge, and then we have demonstrated how it collapsed. Essentially, all the features of the physics we have captured and we have seen. We have also demonstrated how the frequency changes, and then how they coalesce, and that coalescence of frequency essentially indicates the onset of flutter, and that also indicates the setting of aerodynamic damping, which is negative. Okay, right? That's what. And then essentially two modes got coupled, right. So the flexural mode basically pump energy to the torsional mode, right, and torsional mode is the one which is basically triggering the instability, right, and negative damping is coming in torsional mode, right, because you have seen that through the mathematical expression of the respective fluid damping, that the aerodynamic, the torsional mode will allow negative resultant damping, right. Anyway, so there also we have demonstrated the coalescence and separation of this real part and imaginary part of the frequency, but I will just generalize it. So we have seen that we have in a multi-degree freedom system, the equations can be written as mu double dot plus cu plus ku is equal to t, right, is equal to pt, right, and then we can write it in a state space form. I have already written it in the previous example, right. So a state and then y is equal to this is equal to y dot, right, y. So ddt of y is equal to, and then of course there is some excitation, some force, something like this. So here when we define the state variable, this y is a state variable. State variable consists of both the displacement as well as x and x dot, right, x and x dot. So essentially, if it is a 2 degree of freedom system, it initial condition basically, and then of course excitation decides the exclusively decide the state of the system, right. So and then of course what we have seen that here it is asymmetric matrix A in state space form, and then if we want to solve it, this will lead to a quadratic eigenvalue problem if you can convert it. So in both the cases, whatever eigenvalues we will get will be same. This will appear in complex conjugate. So we are defining this eigenvalues, lambda I, right, a plus minus ib, right, or alpha plus minus I beta, whatever, and they will appear in complex conjugate. So then what we so either you can write in state space form, or you can write in directly solve the quadratic eigenvalue problem. And then I have demonstrated to you that if real part of lambda k, if it is less than 0, then of course this is stable. That means this is positive damping. So real part of lambda is essentially associated with the damping, right. This I have mentioned to you, right, that omega k is nothing but imaginary part of lambda k, omega k square rather, okay, and xi k is the damping, damping ratio is minus real part of lambda k, and then this one, right. So then real part of lambda k greater than 0 and imaginary part of lambda k is 0. This is basically divergence. Divergence is nothing where there is no frequency, so system will diverge in one direction, right? So there is no periodic motion, right? And of course positive damping. And then other case where the real part, sorry, negative damping. This is basically flutter, whatever. So that means it is negative damping. This indicates negative damping, and then there are frequencies. So it will perform the oscillatory motion, but it will amplitude will leave. And then when we draw this, in the phase diagram, the change in these two, I have shown you in the previous example, but I will just redo it. With a different, I am assuming that this is for aerodynamic instability, so wind velocity V, but not necessarily that you have to consider this wind velocity. This can be any parameter which is controlling the stability. It can be destabilizing wind speed, it can be for gyroscopic motion, it can be axial force P for the rotating shaft, it for parametric resonance, it can be of course dynamic component of P, okay. Okay, something like that. Okay, so here I have shown to you, right, that how this stick looks like, So I will draw it something like this, So, this you are projecting on the frequency, you see that flutter is indicated by, this is indicate the onset of flutter, because we are plotting the variation of omega with that V. So you see that there is a coalescence of this frequency, and then there is a bifurcation once again, and then once again the coalescence of two frequency, okay, this one, and they are meeting. And then if you project them on the y axis, then they will basically, the locus will be a circle, okay, it's elliptical or something like that. So this indicates these are the flutter regime, you see that, okay. And you see that sometimes the smaller one, this can be very small, the weight for the coalescing zone, okay, coalescing zone can be very small. If smaller it is, smaller is the strength of that instability, and these are called weak flutter and strong flutter. So smaller, if this is called, then it is weak flutter, and this is strong flutter. Weak flutter can be suppressed by increasing the damping in the system, okay, whether strong flutter may not be, okay. So you will see that later, once this aerodynamic, the collapse of Tacoma Bridge, there have been a huge research effort to really understand that what was basically going on, okay, and people started understanding the aerodynamic instability, okay. And there are various means to control the flutter, but then one of them of course by putting additional damping or augmenting the system with damping, okay. So the additional damping will suppress this. So with this essentially we cover all the things, but I will just try to briefly touch upon. It's not possible to explain everything and do, but many of you must have heard of Lyapunov concept of stability, okay. I think it's 1893, something like that, last decade of 18th century. Okay, Lyapunov. So Lyapunov concept of stability, Lyapunov stability analysis, stability. Huh? Here in civil engineering system, or in that matter, this is, we do not routinely follow that because we have alternative way to analyze the system, right? But please note that the concept of Lyapunov stability is very important, okay? And people have used that. If extensively it is used in biology, it is extensively used for financial market, economics. And nowadays, you people are also, many of you are aware about this share trading, right? Share market, yeah. So you are saving, you are multiplying by investing in various shares, right? So what is the stability of share market? That is also through Lyapunov stability. Okay. So there is a difference actually. See what happened as far as structural analysis, structural systems are concerned. Okay, structural or mechanical system. Not that you cannot do a Lyapunov stability, but you have to put. It's an alternate way to do. Okay. So in Lyapunov stability, the way they define stability is something like this. So the way it is written is that there exists, if for any positive, there exists a positive number epsilon, there exists a positive number epsilon for all, there exists a positive number for all, positive number epsilon, which is good. There exists another positive number delta, for which, okay, if the system, so y0, if the system, y0 means, of course, it's a vector, it's basically consists of the state variables, right, y1, y2, etc., right, for a system. So any system, it has a degree of freedom, right, and whatever degree of freedom, you multiply it with 2 because it's velocity as well as displacement, right. So it will have like, u1 0, u2 0, something like n u1 0. So this system is defined like that. These are initial condition, right? Initial condition, right? For a system, initial condition, and it is evolving in time. Okay, time evolution, right? Time evolution. So when it evolves in time, then of course at any time instant, it will have the state variable yt. That means yt will have, things written like y1t, y2t, and ynt. Okay. So it's a basically n-dimensional state variable, right? So n-dimensional state variable. It can be one-dimensional, n-dimensional state variable, state. So of course, for a single degree of freedom system, how many state variable will be there? For a single degree of freedom system, only 2 state variable, velocity as well as displacement. So for how we are defining the Lyapunov stability? So for any system, if there is one positive number epsilon which is greater than, positive, then there exists another positive number delta such that for all, if you take the L2 norm of the initial condition, so there must exist some delta, so that if the norm of the state variable is less than delta, then is less than all epsilon. You understand what I am trying to say? What does it mean? That means you consider you have a n dimension, you consider this. So you have a what? You have a small, consider a 2 degree of freedom system. So it is a circle, right? So you have this the two variable, state variable, right? And they are evolving in time. So, how they are evolving in time? They are evolving in time, maybe something like that, huh? So, Lyapunov stability is defined in a way so that if these two remain within some finite boundary, within some finite, this is bounded by some finite boundary, then at after any time instant, elapsing of any time t, all these response variables remains within a circle of radius epsilon. You understand what I am saying? So, if there exists some epsilon, so that all these response variables, if they are plotted in state space, they remain within epsilon, then there exists some delta, so that all the initial condition remains within this delta. So, this delta, to understand what the concept. So, what it means that this basically implies that if your initial conditions are bounded, then your response can have any timer, they have some bound, you can find some bound for that, you understand. So, it can evolve in time, it can, but it must be bounded within some bound, and that is defined by some positive number, you see that, okay. So, it might have any arbitrary kind of evolution, it can have arbitrary evolution, but as long as it is within delta, it is within epsilon. Now, when it will be destabilized, well, if you go beyond that, then it is not stable in terms of Lyapunov. You understand what I am trying to say, right? And when I am defining L2 norm, it is basically essentially square y01 square plus y02 square, right? L2 norm is nothing but square norms, right? Fine. So, that is defined as the Lyapunov stability, okay. Now, if in limit t tends to 0, if yk tends to 0, then it is called asymptotically stable. This is called asymptotically stable. So, this is the concept of Lyapunov stability, and which is used in many disciplines, widely used, including structural engineering or structural and mechanical system. Now, there of course, it is also applied with a slightly modified version. We can define a Lyapunov stability function, Lyapunov function, okay. So, Lyapunov functions will be, once again, it will be a function, okay, function of function, okay, it is Lyapunov functional rather, okay. So, Lyapunov function, most of the time you will see that it is some form of energy functional. So, if you can define it is positive definite, the way we have form the Lagrangian for a dynamic system, and from there we derive the equation of motion, right. So, Lagrangian can be taken sometimes, can be adopted as a Lyapunov function, you see that. So, positive definiteness of the Lyapunov function will also ensure stability, okay. Yes. So, Lyapunov functional are also used. So, for some system, especially the system which are not discrete continuous system, the system can, you can find out kinetic energy, you can find out the potential energy, and you can form a functional which is Lyapunov functional, and you can ensure its positive definiteness, and then you can assure stability. So, I am not going into much details of the Lyapunov stability or how to find out that, but you see that is the concept essentially. So, why I wanted to mention that I mean without mentioning Lyapunov stability, the discussion of stability is not complete, because this notion of Lyapunov stability is extensively used on all other fields. So, we must be aware about its connection with our structural system as well. You understand what I am saying? So, I will not go mathematical details, but let me tell you something. So, you see, whatever we have learned till now, I mean for all the linear system, if you apply some kind of sinusoidal excitation, then its response will also be sinusoidal, okay, right, sinusoidal or combination of sine and cosines, okay. But if the system have certain some kind of non-linearity, okay, then sometimes its response, you can have a perfectly deterministic excitation, but you have a random, apparently random response. So, this kind of behavior is called chaotic system, chaotic system. So, I will show you a chaotic example system. So, you take a column, okay, and this column essentially is so you apply this load, compressive P is very much greater than P critical. So, then it will be, it will of course, it will buckle, right. Then you put some two magnet here. There is this experiment people have done, okay, north south pole, and then you apply, these are, assume that these are all electromagnet, okay, and then you apply some alternating current, so that there is a reversal in the respective, and you assume that this column is made of iron or those kind of magnet material which can be attracted by magnet, right, maybe made of iron, okay. So, when as soon as it is greater than P critical, it will buckle, so it will be full of geometric non-linearity, right, and then you apply some alternating force. You can see if you apply alternating current, then it will have sinusoidal fluctuations in the force, right. So, and then you can put some maybe one laser based here laser based system, laser using laser measurement, you can find out the displacement, you can plot that. So, you will see that as soon as if P is less than P critical, then when you are applying this sinusoidal force, you see that experimental what I am trying to explain all of you. Did you get what experiment I am talking about? This is a column, made of magnetic material, okay, which are attracted by magnet, and by this some kind of arrangement, of course, you can put some bearing and etc., and then you can apply different force. So, you can apply P, you can change P, you can make P by tightening. This experiment can be very simply done in structural engineering lab. It's not a big deal, very simple. So, P can be greater than P critical, P can be less than P critical, and larger is P from P critical, it will have larger degrees of non-linearity, geometric non-linearity, right. It will be, you have all this in the elastica, I have discussed the elastica, the stability behavior, and then you apply alternating current, so by using this magnet, right, to apply. So, you will see that when P is much lesser than P critical, if we apply excitation force to be sinusoidal, its response will also be sinusoidal or cosine. So, if there is a single frequency input excitation, you will have a single frequency output. But as it is greater than P critical or even more than 1.2, 1.5 P critical, you will see that initially it will be very simple, something like this, assume that there is no damping essentially, but when P is very much P critical, right. But you will see as soon as P is very much greater than P critical, then see your input excitation is purely sinusoidal, but what is your output excitation and what is the output excitation? I am assuming this is the deflection. This is the deflection here. That deflection you can measure using some laser based displacement displacement measurement system. We have one in the lab. So, UT. So, here you are plotting with time, you are plotting UT, displacement UT, okay, UT. So, our excitation is purely single monochromatic, meaning single frequency, sinusoidal, but our output excitation is purely random. Do you see that it's random? What it is called? How it, can you explain that? Why this thing is happening? Anybody has any thought process? Non-linearity, of course, that's good that it is attributed to non-linearity, but then a non-linear system shows random. Many of you must have, you have studied little bit of random vibration, right? Dynamics. See, random vibration means there the input excitation is also random and the output excitation has to be random. But here, because of system non-linearity, this becomes so apparently random, right? But actually this is not apparently random. This response is called chaotic response. Chaotic response. And this gives rise to a completely different theory, which is called chaos theory. Okay. Although it looks apparently random, but actually it is not random. There are hidden order in this. Okay. So the difference between a random, random signal and a chaotic signal is that this is the chaotic response, not random. It is there are hidden order. There are hidden order. How you can explore hidden order? There are various mathematical techniques through which you can find out the hidden order, and this hidden order in that is the basically subject of chaos. Okay. So the hidden order in chaos are find out by of course one is that phase space representation. There is a technique called Poincare map. Then there is something called Lyapunov exponent. So any time series, any random signal can be analyzed for its Lyapunov exponent. Okay. I will explain what is that Lyapunov exponent, and there are other things that you can also do the bifurcation diagram, and maybe another is that power spectrum analysis. So this itself is a subject to be taught separately. I am not going there, but what I am trying to emphasize it to you is that although it looks random, but actually it is not random. There is hidden order behind that, and that hidden order can be explored using different kind of representation such as space representation, Poincare map, Lyapunov exponent. Why I was particularly interested in pointing out the Lyapunov exponent, that is because see, we all studied Lyapunov theory, right? Lyapunov concept of stability. So I tried to establish that connection. So Lyapunov exponent is nothing but that's what I want to explain to you. Okay. See, for any now how to calculate Lyapunov exponent, that is little involved. That I mean in this course it's not possible to explain that thing, but any of this system there is some representation which is called phase space representation. Okay. So any random signal can be have phase space representation, that I will explain simple, and from there using some algorithm can calculate the Lyapunov exponent. So Lyapunov exponent shows basically divergence of that signal. Okay. That means how there maybe there is one trajectory, how that trajectory is diverging. Okay. So that is, so if it is you have a negative Lyapunov exponent, that is associated with chaos. That means it implies that the trajectories are well diverging. Okay. So that is, see, chaos doesn't mean that it will lead to instability, but chaos is some form of instability, some form of, because see the apparently random response, right? Okay. So people have studied this chaotic behavior. In structural system it is not that important because as far as structural engineering is concerned, but for many mechanical engineering systems this is important. Okay. Now, what is phase space? Let me explain to you. I am assuming that this is a sinusoidal excitation, a sin omega t. Okay. Then, if I take derivative x dot t, then what you will get? A omega cos omega t, right? So, if I write x by a square and then I am writing x dot by a omega square is equal to 1, right? So, what it means, x square plus x dot by omega square is equal to a square. So, if I plot it here, I am putting x here and I am putting and this is x and this is x dot, right? So, x dot. So, here you will see that this kind of thing so well getting, right, isn't it? So, we do not see, although there is time variation, see they are varying in time, but when I am doing this representation, I am essentially I am putting this truth state variable and they form a kind of ellipse kind of structure, right. This is called phase space representation. So, you will see, so now, so for a damped system, free vibration damped system, how it will look like? See, initially you started with some displacement and then gradually it is spiraling, ultimately going to, it is merging to the origin. It is a damped free vibration, free damped vibration, right. There is no external force. Do you see how the phase space is represented? This is coming to a point, right. So, now what happened is that when you want to discuss this system, you see that, so you understand that all the dynamical system can have a alternative representation other than the time history, and that representation to space, and this is extremely important for nonlinear dynamics, okay, because that indicates as far as stability is concerned, you will see. So, for any aerodynamic stability, when what is going to happen, you see that, say assume that you are having, so this for the, so ultimately, you see the amplitude is going to be more and more, right. So, it is going to diverge, you see that it will going to, so that will be a, say I am considering a system which is what, subjected to dynamic instability. So, that you see that is increasing. So, that means it is, see here it is damping, positive damping, right, here it is negative damping, right. So, it is increasing, it is so phase space is expanding, it is a ever expanding phase space, understand that, right. Now, of course, in this, so this of course this indicates its flutter because it is through negative damping, flutter negative damping, this is negative damping. Now, the same thing from here, assume that it is coming here, but from here it is having like this kind of things, then of course, this will be have divergence. It is no more, it is, see flutter is associated with what, periodic motions, right, but divergence is not. So, if it diverges, it is something like that, right. Now, what happened for the chaos in chaotic system? So, if you plot, see not necessarily that it will have only 2 degrees of freedom, x start, it is a single degree of phase space because only 2 variable. You will see that it will have, you see that whenever it is getting somewhere attracted somewhere like this is called attractor. You see, in chaotic system, it will be, there will be multiple, why there is apparently random response? It has multiple equilibrium, alternate configuration, okay. So, depending on the excitation and then amplitude of excitation or non-linearity, mobilization of non-linearity, it will reach to different point in the phase space, and then it is very irregular kind of geometry of the phase space, and that's why these are called strange attractor. Strange attractor. So, there are many other things people try to characterize this strange attractor in the phase space. So, using like some fractal geometry and others, okay. Have you heard of fractal geometry? Dimension of one dimension, 2 dimension, 3 dimension, but there are, fractal dimension in which the dimension will be 1.2, 1.5. So, these are called fractal dimension. So, that this will have fractal dimension, and this has a basin of attraction and others, okay. Those I am not going into details, but this is the way it is, okay. So, any chaotic system we may have the chaotic system. So, you will see that for a system to be chaotic, the system must be non-linear. A linear system can never be chaotic. You see that? So, it is the non-linearity which is basically triggering this apparent randomness, because it will have multiple alternate equilibrium configuration, and depending on your excitation and things, initial condition, it will reach to one of this state, okay. And then it can jump from one state to another, during the course of motion, and that's what, there are different kind of phenomena that is called, there are phenomena like intermittency. Like for fluid system, this kind of phenomena occur for turbulence. So, and from, from laminar flow, when you go to turbulent flow, in between the transition is accompanied by such, because non-linearity, there is huge non-linearity, so, convectivity of acceleration is non-linear, right. Because of the non-linearity, turbulence occur, and then with increasing Reynolds number, what happens is that you will see that nice signal, but suddenly there is a huge spike. That huge spike is nothing but from one to another, shifting in the, space of space of alternate equilibrium configuration, and then gradually there will be occurrence of this, sudden burst, okay, and then ultimately it will lead to this turbulent kind of motion, okay. So, stable to, so that also some kind of instability, okay. For structural instability, don't go to the, see what happened is that here I will tell you something. For a single degree of freedom system, you have a 2 dimension, but please consider that you have a multi degree of freedom. If you have, million or minial degrees of freedom, right. So, you can have a reduced order model, but even if your reduced order model, it has 2-3 degree of freedom, you will have a 6 dimensional space. So, those are called hyperspace, okay. And then in hyperspace, there you will not possible to measure all the responses. So, you have to construct this phase portrait, using several algorithm, okay. Those are called, there is something called Taken's embedding theorem, okay. So, those theorems you can use to have a qualitative representation of the phase space, and from there you can extract the stability information, okay, through Lyapunov analysis and others. So, those are research things and a little more advanced. One of my student worked in that area actually in his PhD. So, but some of you may be interested, if you are interested, then you explore of your own, okay. But these are interesting things, okay. And from civil engineering perspective, I think people can contribute, because the problem is that not many civil engineers work in this area. You see that? I don't find anybody, at least in India, that who works in this area, okay. So, the system of chaos and nonlinear dynamics itself is a huge subject, okay. Anyway, so till now, so I will just try to Yes, I will not solve, but I will just show you another example, and please, I will not solve it completely, but I will just, and then with that I will basically conclude dynamic stability. I think we have done enough dynamic stability, right? So this problem you try to solve yourself, but I will essentially write down the expression. Have you solved this example in your dynamics course? Equation of motion, this one? Have you done? No? So this is a mass, spring mass system, stiffness is K, and this is mass M, and this is, you are applying some force here, this force is P, PT. So you are asked to find out what's the stability of the system. Okay, I will not consider stability, but I will essentially write on the equation of motion, and rest of the thing you can do yourself. Okay, so of course this 2-degree freedom system, let us define the angle theta here. Okay, and if this angle is theta, and then you can understand for small theta, and still we assume the theta to be small, small theta, and then u is also small, you will have this from equilibrium configuration, it has this deformation ut, the angle is theta, then this is L sin theta, and then if of course this from this it comes this this one, and then here this one is L1 minus cosine of theta, and then this is nothing L theta square by 2 if you and then if this angle is theta, then this we can take, this one is L theta, L theta, L sin theta, right? So it's we are essentially, there are 2 degrees of freedom, one is ut and then one is theta t, right? Right, ut and theta t. So I will once again, you see that for this system to, so essentially spring mass system is basically performing motion. Okay, there is some applied force Pt, which is restrained by spring of stiffness K, and then it's attached with a pendulum. This arm is rigid, and then this is mass, concentrated mass A. Okay, so you can clearly understand what is the kinetic energy T. Kinetic energy is half let's assume this is M1 and this is M2. This is M2. Okay, half M2 u dot square plus half M1 L u dot plus L theta dot square. So you see that here it is only u, but here the deformation will be governed by AUT plus L theta, right? And a strain energy half Ku square plus strain energy is you can see that this energy, potential energy will also contribute, right? This one, so half Ku square plus, in fact, instead of potential energy, so M1 G L theta square by 2, mgh that contribute to potential energy, and the work done is nothing but P into U, work done by external load P. Okay, that is being applied. So then the total potential energy is half K x square, half K U square plus M1 G L theta square by 2 minus P into U. So the Lagrangian, if you define kinetic energy minus potential energy, right? So half M2 U dot square plus half M1 U dot plus L theta dot square plus half K square minus M1 G L theta square by 2 plus P into U. And you can write down the equation of motion. So del L by del U minus ddt of del L del U dot is equal to 0. There is no dissipation. So of course, U with respect to u you write, and then another equation you will get with respect to theta. So, del L del theta minus ddt of del L del theta dot to be 0. So, these two equations you will get, right. Once you form the Lagrangian functional Lagrangian, then you can derive that. So, I will just write down these 5 equations, and then so the first one you will get, you see the essentially you will m1 plus m2 u double dot plus m1 L theta double dot plus u is equal to p, this is one, and another one is u double dot plus L theta double dot plus g theta is equal to 0. Okay. So, these two equations, so if you write in matrix form, this in matrix form, essentially what you will get here is m1 plus m2 m1 L 1 L u double dot theta double dot plus k 0 0 v u theta is equal to p and 0, right. See that that's a coupled system of equation, and then now you can assume the solution. Of course, you have to find out the natural omega, right. So, you can assume, you see that. So, you are following, right, what I am doing, right. So, you can assume, the solution to be in this form. Assumed the p0 e to the power I omega t, u as u0 e to the power I omega t, and theta is theta 0 e to the power I omega t, and then substitute. If you substitute, then you will get an equation in omega square in terms of other variable, and then once you get in terms of omega square, then you please see that whether there is any possibility of dynamic instability in the form of divergence or flutter. Okay, that you can do yourself, right. Okay. So, with this I would like to conclude the discussion on dynamic instability. Okay. We have solved a number of problems, we have explored the various possibilities and the avenues of dynamic instability. We have also discussed, of course, it's just very briefly, all the formalisms are available for treating dynamic instability problem, and basic stuff on dynamic stability, I think what is possible in the the class. So, now so I am going to go to now the last chapter, this discussion, at least whatever, because we essentially confined our discussion to elastic system. We are not going to consider inelastic stability. That doesn't mean that system cannot go, inelastic system or elastoblastic system doesn't show stability. In fact, the system for elastoblastic stability and others is a huge subject actually, especially for geotechnical mechanics and to certain extent in structural mechanics as well. Okay, especially in concrete and other, which shows this strain softening behavior. Those things you are little more involved and complicated, and separate discussions are required. But at least as far as the elastic stability is concerned, I am going to cover the last thing, and I will give you some overview, because that have very important implication for design. Okay, so last chapter is on stability of cell. So, we have discussed stability of plates. So, cell structures, many of you have attended a course theory of plates and cells. So, you know basic mechanics of cell and why cells are important, and also you are exposed to the bending theory of cell, right, various bending theory and the simplification and implication. So, cells, as you see why cells are important, and then it is said that without the discussion of cell, and if you don't know cell, then you don't know structural engineering, and also you don't know mechanics. Okay, so cell is the most complicated and most it has a very integrated mechanics. Okay, the discussion on the physics and maths involved in cell theory, both in the bending of cell as well as the buckling. It's very interesting and very complex. So, there are very interesting phenomena that occurs, and that is nothing but in the manifestation of stability, manifestation of non-linearity. We will cover them gradually one after another, but what is most important to start with is so cells are two-dimensional structures, and which are characterized by its two dimensions which are much larger than the third dimension, the thickness, right, and it is characterized by curvature. So, why this curvature? This curvature basically helps in establishing a balance between the bending action and membrane action, right. The way you have seen your arch bending of arch, right, you have seen, right, arch bending, right. So, in what happened there in arch, that your bending moment is reduced by the axial thrust, right. So, that helps in reducing the bending moment, right. So, the same thing is basically exploited in two dimensions, right. But the problem with that is that because of the thinness of the one direction, right, like plate, it is also susceptible to buckling, okay, and that's what. So, cells must be designed against buckling. So, that's why cell buckling is a very important thing, and unlike others, we always take example of the cell buckling. Why? Because we have seen, let us go back to our first discussion, that we have shown you 4 kind of systems, right. So, a third kind of system where you have seen that a system which is showing this stable and unstable asymmetric bifurcation behavior, and one limb is stable, another limb, the ascending limb was stable, descending limb was unstable, and it was extremely imperfection sensitive, notorious, because it follows 1/2 imperfection sensitivity. Can we recall, right, that that example? Right, and then we have like these are the kind of, isn't it, this kind of system. So, this system essentially this are, although these were for the toy system, simple system, but cell demonstrate those kind of behavior shows. Another thing is that this, and there will be multiple mode, symmetric mode, anti-symmetric mode, and they are all coupled through geometric nonlinearity, okay. And that's what, because of this modal interaction, I have shown to you, right, one very simple example. We have taken Auguste's column, a column in which two buckling mode interact, and when individual mode, I have demonstrated that although individual buckling modes are imperfection insensitive, they follows 2/3 power law, and then buckling critical load increases with imperfections. But as soon as they are coupled, because of this modal interactions, they become this imperfection sensitive. That means the critical load reduces with increasing level of imperfection, and that becomes 2/3 imperfection sensitive. So, all these cascading things, they have a cascading effect on the aggregate cell behavior, okay, and that's what, there is a huge drop in the critical load, So, that was initially not explained by the whatever linearized theory, cell theory you developed, was developed at the time. None of them were able to explain the huge experimental drop that was observed in cell. So, cell, if you either you take a cylindrical cell, or you take a spherical cell, or you take a conical cell, go and test it, and you will see that the kind of critical load that will be shown through experiment will be much below the theoretical critical load through what you obtain through linear rigid analysis, and that was not explained until later. It was explained by a group of researchers, okay. They have to incorporate there are three important things in that for cell buckling. One is pre-buckling nonlinearity. Unlike others, very before buckling, there are huge nonlinearity in the system. You have to take pre-buckling nonlinearity, you have to consider modal interaction because of geometric nonlinearity. Okay. So, all these things has a cascading effect on the reducing the load. So, the first thing, of course, we will start with the simple cell theory, and then I will show you the basic example of axis symmetric buckling, but this is for just purely academic exercise. Please note that this behavior will never be observed, okay, and why it will not be observed, that I will explain. So, first thing, let us discuss, this is axis symmetric buckling cylindrical cell. So, we are going to consider a cylindrical cell geometry here. So, then here the way, so when it is, I am considering axis symmetric buckling, the kind of buckling that you will observe, is something like, something like this. You see that, right? And along with that, well, I mean, it has to be axis symmetric. Okay, please note this. So, axis symmetric the first thing, and then so there will be of course axial strain along with that, because of out of plane bending, axial strain, axial strain due to out of plane bending. And there will be another strain that it is being compressed, you see that. So, if you just cut it, one of the section you just cut it, okay, and you just see it here. So, and so radius r, and then the radius is increasing to r plus u, okay. Then, so there will be some radial strain, so there will be radial strain, right, or radial strain. So, that we are going to consider here. So, when we are considering axis symmetric buckling of cylindrical cell, what we are taking a simple say a strip here, okay, and please note that in cylindrical cell it is characterized by the single curvature, the curvature along the circumference, right, other direction there is no curvature, it is infinite radius of curvature, right. So I am just taking a simple strip here. You see that, and my coordinate choice of coordinates axis. You see that a longitudinal axis, x axis, right? And then circumferentially in y, and z is outward axis. Okay, along the across the thickness, right? So you see that there is a single curvature there here, right? And these curvatures, so ny is basically the inclined forces along the circumferential direction, right? This must be an angle, and if we take a simple strip that theta is equal to dy by r, so ny 1, 2, and then it is subjected to axial force, okay, nx. So here it is subjected to nx compression, nx. So you see, if we consider equilibrium, right? So circumferential normal strain, this is circumferential normal strain, right? And so if the normal strain is, so then respective in-plane forces, so respective in-plane stress forces, in-plane force E multiplied with thickness E, and then I am assuming the thickness is H, okay. So E W R in H is the thickness, cell thickness. Fine, in-plane forces, and this NOIY, it will have some outward force, resultant force, right? So NOIY has inward resultant force, inward component, that component is NOIY to dx. I mean, if you consider this small section, this is dy and this is dx. I am considering as equilibrium of a small section. So d is dx and this was dy, NOIY into dx, and then dy upon r. Because of this angle theta, you see that inward component, okay. So we can write this effective axial force Py will be, right, nothing but P dx dy so you can write down the equilibrium equation, okay, equilibrium. We will take help. See, the bending is only with respect to x axis, right? Bending, so that's what I will not include. So you see d lambda square wxy was something, that's what we have derived, right? But here the bending is with respect to xy, so I will only include this term, right? So of course you see that this P we are writing if there is some external forces, but there is no external forces. P is essentially 0, right? So that will be the governing equation. So this equation can be solved, okay, to obtain the. So next class we will do, okay.